Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper from the Hugging Face trending list, published on July 2nd, 2025, so just about 6 days ago. This paper introduces a new model that surpasses existing open source and even proprietary models on a wide range of embodied AI benchmarks. The paper is titled RoboBrain 2.0 Technical Report, and its goal is to build a more capable AI for real-world robotics. The authors present an embodied vision language foundation model, which is a type of AI designed to perceive, reason about, and plan actions in physical environments. On Hugging Face, you can find the 7 billion and 32 billion parameter models. The pages include model weights and point to usage examples to try them out. So the key challenge here is bridging digital intelligence with physical intelligence. And this first figure really drives home how the new model tackles this. It shows a series of bar charts, comparing RoboBrain 2.0 against other leading models. The charts are split into two groups: spatial benchmarks, which test the AI's ability to understand object locations and relationships, and temporal benchmarks, which measure its skill in planning actions over time. Across the board, you can see the bright blue bar for RoboBrain 2.0 is significantly taller, showing it outperforms all the others. So, to get a better sense of what these capabilities look like in practice, this next figure gives a great visual overview. It breaks down the model's skills into 4 key areas. You can see things like long horizon planning, which is the ability to break down a big command, like make a burger, into many smaller steps. It also shows closed loop feedback, where the model constantly checks its progress and can even decide it needs to replan. Then you have spatial perception, like identifying a specific hammer, and temporal perception, which involves predicting the exact path to pick up a cup. So, how does the model actually achieve all this? Well, this diagram lays out the architecture. On the left, you can see it takes in a ton of different information, not just text instructions, but also multiple images, video, and even a scene graph, which is like a structured map of all the objects and their relationships. The visual information goes through a vision encoder, which basically translates what it sees into a numerical language. All of this gets combined and fed into the main RoboBrain 2.0 LLM decoder, which does the heavy lifting of reasoning and planning. Okay, so to make that architecture so capable, it needs the right fuel. And that's the training data, which this next figure breaks down. The data is split into 3 main types: general knowledge, temporal, or time-based tasks, and a huge emphasis on spatial perception. The bar chart shows a massive amount of data for things like spatial understanding and spatial referring, which is basically teaching the AI to connect language to specific object locations. This diverse data is used in a progressive, 3-stage training process to build its skills from the ground up. This table then details the configuration for that exact process. We can see the 3 stages laid out, starting with supervised fine-tuning, which refines the model on a huge set of labeled examples. Stage 2 continues this with more specialized data. Then, Stage 3 introduces more advanced techniques. First, chain of thought fine-tuning, which teaches the model to reason step by step. And finally, reinforcement fine-tuning, which rewards the model for good decisions. You can see how they carefully adjust settings like the learning rate, making it smaller at each stage to progressively hone the model's skills. Moving to the results, this is where we see that 3-stage training process really pay off. The performance is compared against other top models on 5 different spatial reasoning benchmarks, which are tests designed to measure things like understanding object locations and relationships. You can see the models are split into general ones, like GPT-4 and other embodied models built for physical tasks. Looking at the numbers, the RoboBrain 2.0 models, highlighted in bold, consistently achieve the highest scores across almost every single test, demonstrating just how effective that specialized data and training was. So, to wrap things up, what we're seeing with RoboBrain 2.0 is a major step toward closing the gap between digital intelligence and practical, physical intelligence. The key takeaway is how it combines massive, specialized datasets with a progressive training strategy to give the model a deep understanding of both space and time. The researchers plan to integrate this into vision language action frameworks next, which are systems designed to translate high-level goals directly into physical actions. This work really pushes us closer to creating truly generalist embodied AI. That's all for this week's AI Research Roundup. Thanks for tuning in.